Okay, so far we have discussed about how to model our noise, okay, by using several noise model which is depend on the shape of PDF, and that PDF is it is obtained from the histogram, and that histogram is obtained from the image you capture, where that image should be a plane image where it consists of very homogeneity pixels there. And that is actually we already finished this part. Okay, we already discussed this part. I will like to highlight this thing again. Okay, when we discuss about the noise model, actually we are already finished discussing this part, which is the degradation part. Okay, and still we are in in phase 1 or condition 1, where we assume that our image is only affected with noise and it's free from degradation function. Okay, so once we have identified type of noise or noise model that affected our image G, then next process would be the next process is we want to identify what type of filter that you can represent here as a restoration filter to be used for the purpose of to enhance your image which is affected with noise here, which is the G, and you produce this image F height. Okay, again, like I mentioned previously, our objective, we want to find a suitable filter to be put here, and that filter will actually improve or restore the information that have been degraded by this noise, and produce the F height where we want to have our F height as close as our F over here. Okay, now in this video we're going to discuss several filter that you can use as a restoration filter, where it's depend on what type of noise model that you identify before during the degradation part. Okay, the first filter that you can use as a restoration filter is called Arithmetic's mean filter. Okay, Arithmetic's mean filter is the one of the simplest mean filter, and actually this is the equation. So you realize that now this is how the equation have been expressed. As you can see now, G is not the output image anymore. Now G will become your input of the filter, and F height is the output. So that's why I always highlight this thing. Okay, during image restoration, actually G, if you talk about image enhancement, okay, this is actually our F. Okay, because previously when we talk about F is actually the input image, and then any output from this process should be your G. However, for restoration, then we change the notation, because our F, we already used the F to represent the digital image that free from any degradation factor. However, the one that you receive or the one that you get from your digital camera is your G, where the image, that is the image, represent the image affected with several degradation factor. So that's why now that G will become the input for the process, while the output is F height. Okay, so that's why the restorer one, this expression is represent the arithmetic mean filter. So now the input is G, the output is F height. Okay, and another things I would like to highlight here, okay, before we go deep into what we have discussed after this, we have a lot of filter there. Okay, this one, okay, the arithmetic mean filter actually is also known as our average filter. Okay, the one that you learn in image enhancement, average filter. Actually, if you compute the average filter, and you will get the same output as arithmetic mean filter, because both are the same filter. Okay, in image restoration we call that filter as this filter as arithmetic mean filter, while in image enhancement we call as the average filter. Okay, for that kind of issue, let's now I would like to invite you to discuss about this, okay, through in detail in my whiteboard. Okay, now let's take a look at this whiteboard. Okay, again, we're still talking about the phase one where the image is only affected with noise only, and then in this video lecture, we're going to discuss about several type of restoration filter, and one of it is arithmetic mean filter. Okay, then I write it that in my whiteboard, there's arithmetic mean filter is also known as average filter. So how we gonna prove that the arithmetic mean filter is also known as average filter? If you see the equations there, okay, this is the one that in the slide that I showed previously. Okay, that this is arithmetic mean filter equation, and this is actually your average filter when you want to compute something. And the question is how this thing and this thing is similar, because when you see the equation there, it's a little bit different. Okay, one thing that I also like to highlight here is that now I use G as an input and F head is the output. Okay, for this one, so now it's a similar notation there, so you might not confuse there. Okay, don't confuse with this one. Now I just, because I want to make sure this one is tally with the our previous our current chapter, so that's why now input is G and the output is F head. And if you want to apply the filter, which is my average filter, which is this one, then I need to convolve between the G and my kernels there. Okay, and then you need to perform the convolution. And the question is, how does these two things is similar? Okay, if you remember, when you learned digital signal processing or biomedical signal processing, that you deal with one-dimensional digital signals, if you remember that there's two terms there. Okay, actually, if you talk about one system, you can represent the system in form of a convolution operation like this, and you can also represent the system in form of what we call as a different equation. Okay, different equation. What is different equation? Different equation is you are actually develop the equation where it's only consists of the relation between the input and output. So that's why if you can see over here, you only have the input which is G, and then the output which is F head. There's no involve the convolution process or the kernel here. So in other words, actually this one is in form of convolution operation, meaning that you know that to obtain your F head, you need to convolve between your G, the input, and the filter or the kernels there to produce this one. While this one actually is the same thing, but you are actually removing this thing in the equation, but actually this internally here, it's actually the computation that is internally done there. So that's why the form is only consists of the input and the output. So if that equation is that form, then it is also called as different equation. Okay, the terminology for this one. Okay, let's go to the next line there. So if you remember, okay, again, this is our system. Okay, the basic system there represented by this block, and again this one is also known as your transfer function, or in image processing we call it transformation function. Okay, transfer or transformation function, doesn't matter, it's referred to the same thing, transfer or transformation. Okay, transfer or transformation function. And if you remember, then actually how from here you can convert into this version. Actually you have learned that in your previous course. Okay, I give you some example at this line over here. Okay, this one. Okay, this is the form, this is the expression. Let's assume this expression is actually represent this system. Okay, and if you see the on your left hand side is the output, and the right hand side is the input, which is the X. Okay, this is input, this is output, and there's no convolution involved. then that should be in form of different equation. This is what we call as a different equation. Okay, if you remember when you learned this topic, you can change. Okay, you can also convert this expression from the represented this system to represented the system, instead of using okay, given the system is represented by this expression where it is in form of different equation, then can you convert this one into this form, which is in form of convolution. And one of the common way to do that, if you learned one-dimensional digital signals, okay, you need to learn you need to know about the Z transform. Okay, this is under Z transform. So that's why you see there, one way you can express this time domain, you convert it into Z transform. Okay, and then this is how we express in Z transform. And then if you learned the analog signal, then Z transform will become Laplace transform. Okay, it's the same thing. Laplace is for analog signal, Z transform is for digital signal. So if you convert into this way, and then you factorize here, you arrange back like this, and then at the end, you know that once you this similar to frequency domain, if you in the Z transform, then you can every convolution will become multiplication. So that's why from there you know that in order for you to obtain your Hz here, which is the Z transform of Hn, then you need to divide between your Yz and Hz, and then from there you know this is what you get, and then from here you arrange back this one, then you get this is my expression, the expression of that represent my filter, which is my Hz there. Of course, the next process you need to apply the inverse Z transform to convert it back to the original filter in time domain, which is Hn, and then that's how you get back your expression in form of convolution operation. Okay, so I hope this discussion can you know, you can relate with this thing, okay, that you will learn in image processing. And again, like I said, arithmetic mean filter, this one and this one is similar. Okay, this one is in form of convolution operation, while this one is expressed in form of different equation. Okay, so I explain this thing because I want to show you the terminology there between one-dimensional and two-dimensional. Actually, these are similar things. However, don't get confused there. Don't worry about this example, because in image processing we will not highlight, or we will not ask you to convert this one into this one. Okay, I just give you some idea. Actually, both arithmetic mean filter and average filter is the similar things, and the issue is why average filter you learn this is the equation, and why arithmetic mean filter when you learn this is the equation. Actually, they are the same thing, only represent by different version of expression that represent the same operation. Okay, one is represent in form of different equation, another one is represent by in form of convolution operation. Okay, but I have proved to you, actually you have learned that before in 1D, where in order for you to change from the in form of different equation, you can use a Z transform, then you can convert from here to here. Okay, next process, let's try to understand what actually how actually to translate this expression, because there's a lot of things there. Okay, and then after that I will try to prove to you that actually this is actually also similar to average filter. Okay, how I will try to prove to you how actually this mechanism or computational expression actually perform the same operation as your average filter. Okay, now let's take a look at this thing. I already draw it here. Okay, it's the same equation that represent your arithmetic mean filter, this one. Okay, this is just assume this is your input image, which is your G. Okay, then you realize that in this equation they are not using index of xy, they are using s and t, so there's a meaning behind that. Okay, now let's try to interpret one by one each notation here. Actually, this is your the m and n here is this one. Okay, this is m, this is n, which is the window size. Okay, for this example we are using the window size equal to 3, so 3 times 3, so so that's why I label my m is equal to only 3 pixel, n is equal to 3 pixels. Okay, from there you can see that in this expression the s and t is a subset of this this surface, which is a capital S, represented by capital S xy over there. So why they put st here? Actually st is I can consider as a local index instead of global index. The global index is this one. So when I say global, is refer to the entire image. However, the st here is represent the index which is under or overlap behind window size. Okay, in this case let's assume this one m and n we are using 3 times 3, so m equal to 3, n equal to 3. So this s xy over here, the capital xy here, is represent the surface of the window. Okay, which is in this case is this one. Okay, that is your sxy, but for this case this one is not just sxy, this one is x11. Okay, means that when your x equal to 1 and your y equal to 1. Okay, because so that is how when you want to find, for example, okay, no, let's assume this is 1 2 3. Okay, we are using index, we are using matrix, so this one should 1 2 3, this one is 1 2 3. Okay, so this one is s when you want to find f hit 2 2. Okay, then from this equation you need to express the formula. This one assume our m equal to 3. Okay, n also equal to 3. Okay, then this st, okay, the s and t, to find this one, then you need to put this st is a subset of a surface capital X 2 2. So what is the meaning by 2 2 here? Which is this one. Okay, which is this one. Okay, okay, this one should be your S22. So I change this xy because this xy is according to this xy. So is this xy is 22, then this one is called S22. Okay, so now if you go back to this equation, so is this one is S22, so your st here is a local coordinate, meaning this one. This is S1 T1, this is S2 S equal to 2, T equal to 1, this one is S equal to 3, T equal to 1. So that's how, so meaning that this is the index of the S and T represent the coordinate, the local coordinate that involved inside this window. Okay, so in other words, that's how you express. So that's why when you understand this equation, now it will become something like this. Okay, if I want to find my f hit there, my f hit f22, then is actually is 1 over 3. Of course 3 times 3 is 9. I just put it 9 because m times n is 9. So now that summation, this summation, okay, g s equal to 1, s equal to 1, meaning this one a. So a, so you must put a bracket there. Okay, let me try to write here equal to 1 over 9 then you have your A plus B, okay, because of summation you are plus B, then plus C plus E plus F until K, okay, the one that inside the red box there represent by this surface S22. Okay, that's how you calculate. So at the end you are plus together A, B, C, E, F, G, I, J, K divided by 9. Okay, that is if you want to find F22. Then of course that is only for F22, this point. How about then you need to go to another step to find the entire image. Start from, after F22, then you need to find another one which is F32. Okay, to find the F32 again you need to repeat the same thing, 1/9. But the one that I want to highlight in this equation is that now to find this one, then you need to use the S32. Okay, so where is S32? So S32 is over here. So let me use another color there, this one. Okay, this one is S32. So in other words, you can see this equation, even there's no convolution, you cannot see the convolution representation in this equation. And if you remember, if you convolution is something very special. Once you do some convolution, you need to remember one thing is that you need to do two things there. Okay, when you do a convolution, one is you need to flip. Of course, we have discussed before in the previous chapter, flip have been skipped because of the symmetrical structure of your kernel. And then another things that you need to remember, convolution also require you to translate the window to the from the top left corner to the bottom right corner. You need to process one for each and every pixel until you process until you process the whole image, whole pixel, okay, in that entire image. So that's how the convolution works. But the question is how this equation represent that translation, the movement of the window. So you can see here, the one that move this window, okay, is the surface is this one, which is the capital SXY, because this one will keep translate, because since you can see that your capital S here, XY is this XY is keep vary, where this XY is depend on the XY index in our F head here. So if you want to find F22, the surface is S22. If you want to find your F head 32, then the surface will become S32. So that's how you do the movement mechanism of that window. Okay, so that is for the movement of that window. So now how to prove actually this one is related to average filter. So you can see here, okay, let's focus on this one, S22. Okay, it's S22, then the operation will become again my it's not F22, my F head 22 actually is equal 1/9 A plus B plus C plus E plus F plus plus G plus I plus J plus K. Okay, so if I'm using an average filter, if I want to find the output of this region, then what I do is of course I will compute the SOP, okay, sum of product. So if you want to compute the sum of product of that region, then okay, again this is my kernels, okay, 1 1 1 1 1 1 1/9. Okay, so I think you will perform the same thing. You put 1/9 and then your A time 1 plus B time 1, and then at the end you also end up with k minus 1, because 1 represent the kernels there inside this one. So in other words, you can see that I managed to prove that even I'm using this formula to compute my f head to 2, I'm using this formula, okay, I'm using this formula to compute my f to 2, I will get the same expression as when I compute my f to 2 using this kernel, because later I will still get the same expression. So in other words, I prove that this arithmetic mean filter is similar with our average filter in image enhancement. The difference is only how you express. Okay, this one is in form of different equation, and that one, the previous chapter, in the form of convolution operation.